Welcome, everybody, and thank you for taking the time out of your day to come see this session on Amazon DynamoDB. My name is Rick Houlihan. I'm a senior practice manager on the DynamoDB service team, and for the last 5 or 6 years or so, my job has really been focused on evangelizing the technology, developing design patterns and best practices. Many of you have already seen my sessions at reInvent previously, and my team is actually responsible for developing a lot of the content that you see in the documentation around design patterns and best practices, for DynamoDB. And a lot of the stuff we talk about is actually broadly applicable across NoSQL. And that's really what we're here to talk to you a little bit today about: fundamentals of NoSQL. What are these basic concepts of these things what we call single table design, right? Partition overloading, index overloading. How do we deal with secondary indexes? How do we design for efficient data models for NoSQL? But this year is interesting. We're online, so we're going to be able to do a little bit more show rather than tell. And so as we get into the design patterns and best practices, I'm going to actually be showing you the code behind and the console operations behind setting up global tables for high volume replication, low latency replications, how to deal with summary analytics and create those streams, Lambda aggregation methods and whatnot. We're going to talk about a really neat technique that I found in the last year or two, which is about right sharding for selective reads. And what that did for one of our customers to reduce their cost, and showing you real life workloads and actual, running applications that are actually doing these things, and how easy it is to get these things set up. So the first thing we want to understand when we talk about NoSQL databases is, what is it? A lot of people don't really know the technology very well. They're just becoming introduced to it. And the thing to understand about it is a lot different than the relational database. It's not a set of tables that we're going to join data across. It's actually a single table that we're going to use as an indexed object collection. What does that really mean? It means we're going to push all of our items from these various relational database tables. They're all going to land in one place, and they're going to have a bunch of different types of attributes. That's why we call it schemaless in NoSQL. It's not really schemaless, but it doesn't require or enforce a schema on these objects, other than there needs to be some sort of unique identifier. In this case, a partition key uniquely identifies the item within a DynamoDB table. When I query the table with the partition key value equals X, I'm going to get an item back that describes the attributes that are associated with that value, and that is the key value access pattern that everyone's so familiar with NoSQL databases. Now, when you add the sort key or create a compound key, we get a little bit of different structure here. Now, all of a sudden, a partition doesn't define a single item. It defines a container for many items, and the sort key defines the uniqueness of the item within that container, and I can model those one-to-many relationships and complex relationships between these items, and I can use range operators on the sort key to deliver and filter the result set. So I only have to select certain items from that partition based on conditions that the sort key attributes actually meet. So this is a way to efficiently query for your data within a grouped collection of items, and it more or less aligns very well to how the relational database uses data, right? When I query the data in the relational database, I'm going to join the rows across a subset of the tables, not all of the tables in the database, but just the ones I need. And applications kind of work that way. They want to use bits and pieces of data, not entire hierarchies of data. So we want to avoid creating these large monolithic objects, because when an access pattern fires, I don't want to read the entire customer history when I only need the events that occurred in the last 30 days, right? Things like this. We want to read and write the data that we need to access to drive efficiency in the system. When you use large objects, typically that's an anti-pattern, and we really want to break things up like this, right? Multiple items in a single partition. So when we start to look at how we can address these secondary access patterns, right? Like if the table has a partition key of customer ID and a sort key of interaction date, it's easy for me to get all the interactions for a customer by querying the table and saying customer ID equals X, interaction date is greater than Y, gives me all maybe customers' orders, shipments, invoices, items, all kinds of stuff. But what if I want to get all the items that are back ordered, for example, or all the orders from a given source? In order to do that, we create secondary indexes. We're going to decorate these items with additional attributes, which we will index to create more interesting groupings of objects that we can then query, to satisfy additional access patterns. When I define an index on a DynamoDB table, essentially what I'm doing is creating a derivative table. As I insert items onto the table, they will be inserted and regrouped on those indexes according to the index keys that are specified, on those items. So what does that really look like when we actually look at the data? This is some data that would describe interactions of a customer, in this case orders, items that were ordered, the customer's metadata. In this case, partition key is the customer ID, sort key is the interaction date, in this case the order date, and concatenation of the order date and the order ID. Again, we need to generate uniqueness. What I'm doing in this particular schema is I'm tracking the items on the order individually as their own objects, and I'm doing this because eventually we might want to index these things on different dimensions. I might want to index the orders by source or the objects by product ID, in which case I need these things to be on different items so that I can pull them out efficiently, to the indexes. I don't necessarily want to project all the order data to the index that I'm querying for, product data, and vice versa. I don't want to project the product information to the index categories that I'm querying for the source data for those orders. This structure works really well because when I query, in this particular case, let's say I want customers' interactions in the last 30 days or whatnot. When I query this customer partition with a date timestamp greater than X, it's going to bring back all of the items in the partition, including the customer's metadata, because that matches that sort key condition. These are string sorts. That's an ISO 8601 timestamp, and alphabetical characters are greater than any numeric character. So greater than timestamp brings back not only the date ranged items that meet that condition, but any item that begins with an alphanumeric, which includes the customer's metadata. So if I land on a dashboard for this customer, logs in, goes to the dashboard, wants to see all of his activity, a single query brings back all of the customer interactions, the orders, the items they ordered, shipments, payments, invoices, whatnot, everything in the system, as well as the customer's metadata that I would use to populate, the top level attributes of that customer dashboard view. So again, one query brings back all that data. That's similar to what we would get if I were to issue a join query against these tables in a relational database, right? I'm going to get the data I need to populate that view. Secondary indexes define additional groupings or derivative tables that we can create and maintain when we insert items to the DynamoDB table. And important to understand when you configure those GSIs to only send the data that you need, right? Some of the data might not be required for all of the access patterns, right? Like might be that I have a workflow that says, get me all the items that match a current condition. I don't need the items themselves. I just need to know which items matched. In that case, I define a keys only index. I'm going to project only the keys, the GSI keys from the items I insert to the table over to the index, and that keeps a nice, very lightweight storage container that I don't have to pay as much to maintain. Again, understand these GSIs, these secondary indexes, these are just derivative tables. If I project all of the attributes from all of my items to the GSI, then I'm going to double my storage cost, double my WCU cost. And that might be fine based on your access patterns. If your access patterns require all that data, that's great. But if they don't, you can save some cost by projecting only the attributes you need. So remember that when you're configuring your GSIs. The other thing to remember about NoSQL is distribution. We need to get things spread out. All NoSQL databases scale the same way. We're going to have some sort of a hash key, some sort of a partition key or a shard key or some sort of a value that we're going to use to lay these items out across some arbitrary key space. In DynamoDB's case, we're going to take the partition key value, we're going to hash it, we're going to lay these things out across this logical range. And when we need to scale the system, this might originally all the data lives on one storage node. Eventually, I need to get more throughput, more capacity on the system. I'm going to chop that key space up. I'm going to spread it across physical devices. And now when I query the system, I'm going to provide a partition key value equals X. And that's going to tell me exactly which part of the key space I need to go query to get that data. I don't need to query every single node across the key space, just the one that contains the data I'm interested in. And this is how NoSQL databases scale. All of them do this. There's some sort of, again, partition key, shard key value we're going to use to lay these items out, chop them up, and distribute them across physical devices. When we start doing this in DynamoDB, it's important to understand that there's a certain amount of throughput that you're going to get for a given storage node. Now, in this case, on our table, a given customer is not going to have a lot of interactions at a high velocity, but if I'm indexing on order source and region or product ID and status, now across all the customers that say Amazon retail, you're going to see very, very large velocity of orders. So if I'm trying to aggregate on the GSI all the orders by region, for example, give me all the online orders in the US, that's going to create a very, very high velocity write pattern on that particular partition key, which would be online. So in order to be able to increase and get that data spread out across multiple keys, I'm going to salt those keys with a random value. Let's say I needed 10,000 WCUs to be able to support 10,000 orders per second from a given customer, or from across my customer base. I would salt the online key with values of 0 to 9, maybe increase that range a little bit, give myself 10 partition keys or more to write those orders across. And when I need to read those orders, what I'm going to do is scatter gather. I'm going to query all those partitions simultaneously and bring back all that data across multiple threads. We can abstract all of this behind a data layer API so that developers don't all need to be aware of the sharding strategies. This is really something your data layer API team would be very in tune with, because we're writing and reading across many partitions. We're using parallel processes to increase the read throughput, but that complication can be something that's abstracted from most of your development team. Now, the other thing we want to do, again, we want to use these generic keys just like we do on the table. When I use PK and SK as my table keys, then every item that inserts the table has to have those keys, and they don't all have to have the same type of value in there. As you can see here, we have 3 items on this table. They all have partition key as customer ID, but they have different sort keys. One is the order date and order ID. The other is the order date, order ID, item ID, and the third one doesn't even have a date timestamp. But that's okay, because they're all strings and they're all named SK, so they all fit on the table. And the same thing with GSIs. If I want all these items to fit on the same table, I need to use generic key at names. And the reason I want to do this is so that those indexes can then support multiple access patterns. Every index is a capacity bucket. I'm going to have to allocate capacity too. If I define named attributes as my typed attribute names as my PK and SK, or partition key and sort key of the GSIs, then only the items that contain those named attributes are going to show up there, and I'm going to have to create another GSI to support that other access pattern. In this case, what I can do is actually overload those items onto the same index, and it's the query conditions that define what comes back. When I query across the online sharded space 0 to n, I'm going to get order items. When I query by product ID and product status, I'm going to get product items. I'm never going to mix the two, because the query conditions are going to prevent me from bringing back the items that I don't expect. But what I'm doing here is increasing the efficiency of this index by allowing it to support multiple access patterns and reuse that capacity allocation across multiple workflows within my application that typically aren't all firing at the same time. So I drive a lot more efficiency in the system by practicing this index overloading, and the only thing we need to do to make this happen is use generic attribute names for our keys. Now, when you think about keys, you should think about them as labels. Here's how I find this object. I'm going to find this object using this partition key and sort key value on the table. I'm going to find this object by using these GSI partition keys and sort keys on a GSI. But they should not really be typed or strongly named, because if I do that, again, I'm limiting the types of items that can be inserted onto that storage container, be it a table or a GSI. All right, so let's take a look at some workloads that we might use to execute high-velocity aggregations. This is a really interesting app I worked on not so long ago. It was a trading aggregation service. This is a data analytics firm. They took data feeds from many trading desks, and they anonymized the data and reported back across all these consumers, what securities were moving at what volume. And so they had thousands of securities that were being tracked, millions of transactions throughout the day. Their highest volume securities would trade at up to 10,000 transactions per second. Across all securities, they peaked at around 100,000 transactions per second, and what they needed was global replication. They had multiple teams in multiple regions producing the data, consuming the data, and they wanted global replication across regions within 5 seconds to have availability of that data across teams. The 4 access patterns to support: get transactions by ID, get all transactions for a security, get trailing 30-day summary for a given security, and get the 30-day summaries for all securities. And so these were the access patterns that they needed. What they wanted was, again, that global replication. That was a real big feature for them that they needed to have. They initially looked at setting this up themselves using some off-the-shelf technologies and balked at the complexity, which actually demonstrates a very mature engineering team. It's not easy to do global replication at scale. And so what they wanted was fully managed. They needed active, multi-region. DynamoDB checked all those boxes. Cross-region replication in less than 2 seconds. As a DynamoDB can provide, their requirement was 5 seconds. So again, beat that. and it deploys instantly in minutes from the command line, from the console, from your code, wherever you need to set up the global table. It's all available for you. So let's take a look at that process. What does it look like to create a global table, and how do we do it? All right, let's take a quick look at how we're going to get this thing set up for global tables. Again, we want to do a high velocity replication for this workload that we're going to be demonstrating, and that's going to happen immediately. I'm going to be throwing thousands and thousands of requests across the wire, and we're going to see how that replication lag, what that looks like. In order to be able to support that, I need a table with a large number of partitions from the beginning. If I go ahead and use the default configuration, which sets me up with auto scaling at a minimum provision capacity of 5 RCUs and 5 WCUs, that's really just going to provision a table with one single partition. It can't handle that big workload, so it's going to actually start to throttle and hiccup. So the way we're going to actually tell the system that we want more is we're going to just jack those limits on those RCUs and WCUs in our auto scaling algorithm, and this then forces the system to deploy a table with a large number of physical partitions. In this case, I'm going with 10,000 RCUs and 100,000 WCUs. That's going to give me 104, 105 partitions when the table's created, and now I can support a very high velocity workload. A reason I'm doing this rather than use just provision capacity is because the auto scaling has to be enabled in order to be able to add the global table replica, right? It's either has to be on demand or auto scaled. So let's go ahead and create the table like this, again with that high floor to my auto scaling algorithm. And now when the tables comes up and it's online, which only takes a minute or so, we've got a big table with a large capacity and a large throughput. Once this table is online, we're going to go ahead and add the global table, right? So there's our 100 partition table. It's all ready for us. We can now add the global table. In order to add the global table, we need to enable the stream. Obviously, as change comes onto the table and writes occur on the table, we want to replicate those writes, which means we need the DynamoDB stream. And then once the stream's enabled, we can go ahead and add that target region, right? So I don't believe I can do this. Yeah, I can't do this while the table is being modified. Yep, there we go. We're actually ready. We can select our target region, and let's say in this case we want to do US East, North Virginia. Region's ready. I can click create the replica. Let's go ahead and use the new version of global tables as we go ahead and create that replica. Now that's going to go to the target region. It's going to create this infrastructure in the target region, and we can actually go to the target region and see that happening. We're not going to wait for this global table to be complete here, but you can actually see what's happening over here. Is this table is now actually being created, right? So this table is going to have the exact same settings as the table in our source region, and we're going to be able to use this for the rest of our demo. Let's take a look at this customer's table design. It was pretty straightforward. They had a table which partition key only by transaction ID. That was the get transaction by ID. They had a GSI where we write sharded all of the updates for given securities into a set of partitions. In this case, we need to support up to 10,000 transactions per second per security. Customer was worried that some sort of trading anomaly could drive that volume significantly higher, so they chose to write shard across 100 partitions just to make sure they had plenty of capacity in case some security went hot. All the transactions were pushed into DynamoDB streams. They used this as an aggregation pipeline to summarize the events, get that data pushed into a summary table, and that summary table supported the other two access patterns, right? Get me the summary by ID, get me the summaries for all securities, right? Select for by PK equals security ID or table scan. Those are the two operations there. The customer had this analytics pipeline, which is a very common process that we tell people to use to generate those operational analytics or summary reports, push the data into DynamoDB streams, read it with Lambda, maintain those real-time aggregations as summary counters on the table. The other access or the other workflow that they had was they pushed those transactions into Kinesis Firehose, rolled them up into S3 as Parquet files, and they could query that raw data by Athena. They didn't really care about the raw data after the given day, the trading day, so they would throw those tables away, but they did need to have the data online just in case. There was some rare access patterns they needed to run to do some triage, research, debugging, and whatnot, and so they wanted that data online. Now, DynamoDB just recently released a great new feature that replaces this whole pipeline on the bottom here. It's copy table to S3, and it works off of your PITR data. So 1 second resolution. I can go into the console and say, hey, I want a snapshot of this table in S3 as of midnight of last night, and it will execute that operation and give you a nice view of the table the way it existed at that time. Again, when this customer implemented, we didn't have that feature. Now we do, so we can eliminate this whole chunk of cost from their implementation. The other thing we did was we looked at their schema and we said, hey, you're doubling your write capacity, you're doubling your storage cost by using this table in GSI. If we use a shaped partition key, so to speak, we can actually eliminate that GSI. And that's what we did. So you take the transaction ID. In this case, we noticed right away the transaction ID included the security ID that the transaction was for. And we actually went ahead and used the transaction ID itself, the hash code of the transaction ID, modulo by the number of partitions, taking the absolute value to generate a partition key for that security. So instead of write sharding on a GSI across 100 partitions, we moduloed by 100 on the hash code of the transaction ID, which gives us the ability to decode the partition. When somebody comes back and says, give me this transaction by ID, I can actually take the hash code of the transaction ID modulo by 100. I already know the security because it's embedded in the transaction ID, so I can pick the partition key and make one selective read to that partition to get the transaction. So again, shaping the partition keys using the sort key value is a great way to be able to selectively read across a write sharded partition space. So now that table supports both access patterns, get transactions by ID, get all trades for security ID, and the only thing you need to do is when you insert the items, take that transaction ID and hash code it, modulo by 100, and use that as the suffix. So in this case, this is what we're doing when we format the partition key. We're taking the security ID, hash code, the transaction ID, modulo 100, and there's where we're writing it into. And on the reverse process, on the select, identifies the partition that we need to query. So very nice way to use that sort key to identify the shard and be able to produce a selective read workflow. All right, let's take a look at the aggregation pipelines that we're going to be running here and how to set those guys up. All right, let's take a quick look at the tables that we've got deployed now. I added the second table to take those summary items. Again, we're taking the transaction data that's hitting the Demo 1 table. We're rolling those up into summaries that we're posting to the Demo 1S table. So let's take a look at the Lambda script that's executing between these two tables. It's not complex code. It's fairly straightforward. This handler is where all the work happens. What happens when you invoke the Lambda function is that we're going to hand it a bunch of records, by default up to 100 records, and this is the key here in the whole, reducing the write pressure on that summary table. As we see high volume transactions coming in for single securities, they're write sharded on the primary table across 100 partitions to handle the workload, but what we want to do is roll all that data up into a top level summary item, and what we're relying on is the fact that those transactions are going to be hitting the same Lambda instance in batches. And so this is what this code actually does. It iterates across all of the records and then summarizes all of those transactions. The individual, it doesn't hit the summary item for each transaction. It basically creates a list of unique securities found in this batch I was handed. And again, at high velocity, that means I'm going to get a lot of records for the same security, and it's going to generate one total summary record. We're going to build an update expression to update the daily totals, and we're just going to increment all those counters by the amounts that we just determined. And then we're going to initialize tomorrow's counters, set everything to 0 for tomorrow so that we can start incrementing those counters as soon as we roll the clock. And then we're going to remove anything that's more than 30 days old because we don't care about that data. And if we leave it on the item, it's just going to get bigger and bigger and bigger and become more and more expensive to read and write. So this is kind of code that's very basic, but it does the job for maintaining those summary aggregations. If you have other metrics, computed KPIs, top end, last end, max min, things like that, we can create code to do all of that. And the key here is what we're doing is we're building an item that can be easily read and doesn't cost us a lot at runtime when we actually need to access this data. We're kind of maintaining it behind the scenes so that view is available for you all the time. Once we're done with that update expression, we just simply iterate through the securities that we found in our record collection, swap the values into the query parameters accordingly, and send the updates, basically acquire a list of promises and await those promises. If everything works well, we go ahead and go get the next batch, right? So again, not complex code, very straightforward code to execute in this particular case. Let's go back to the console and actually deploy it. as we look at the Lambda console, it's a very straightforward process to do. We just need to name the function, assign a stream processor role, let's assign a name to it, and assign an IAM role. And I already have a predefined role that I'm going to use. It's the stream processor role, and we can take a quick look at that. It's very permissive. I would never use this in production. It allows basically access to any resource in my account space and any DynamoDB operation against any table. So we definitely would want to restrict it to the tables you need to access, the operations you need to execute. But for my sandbox, I just want it to work, so I don't really pay much attention to that. And honestly, I don't worry about it. It's not production data. So once we've created the function, we're going to go to the basic editor here. This is a full-featured JavaScript editor, but we're just going to go ahead and paste the code in that we already reviewed. I'm going to deploy that code, and now what I've got is a stream processor function with some code behind it. We've got no trigger. One thing I want to do before we actually execute this workflow is I want to increase the memory to this container, because that 128 megabytes during my testing wasn't quite enough. Things are running at pretty high velocity here, and we were running out of memory and swapping and causing the functions to time out. So if we go with a little bit more memory, what I found was about a gigabyte for my workload. Your mileage may vary depending on what you're doing. With a gigabyte, this process runs much more fluidly. Let's go ahead and add a trigger. Many sources to trigger a Lambda function. The one we're interested in right now is DynamoDB. We're interested in the demo1 table. Again, default batch size 100. That's all we need to do. We can go ahead and add this function or add this trigger to the function. Now we're ready to go. I could go ahead and execute inserts to the DynamoDB table, demo1 table. They're going to fire this stream processing function, and if the data looks the way we expect based on the code that we wrote, we're going to go ahead and aggregate that and send that up to the summary table. So let's go ahead and take a look at what that actually looks like in reality. I've got two EC2 instances here. I've got one up in US East 1. That's the guy on the right. I've got another one up on USOS 2. That's the instance on the left. And the instance on the right is listening for the loader to complete. We're going to run this for 100 securities for 10,000 transactions. And, it's going to scan its local table until it sees those transactions, 10,000. Then it's going to report the lag time it took from the time that it was touched by the source instance. And then we're going to flip the script and do it backwards. We're going to write 10,000 items in US East 1 and send them back to US West 2 and report that as well. So let's see what that actually looks like when we execute that workload. It's really, really fast. As we can see, 1.6 seconds out. We've got 1.3 seconds back, and we're done. Right, 10,000 transactions executed, inserted into the table in a couple hundred milliseconds, replicated across the country in less than 2 seconds, and that's what the documentation is going to tell you, 1 to 2 seconds for replication lag for global tables. Let's take a look at the actual data on the table now. We've got the summary items that came through. They've been updated, again, in near real time, 1 to 2 seconds from processing from the time it hits the table to the time the stream processor completes and executes the summary update. We can see that each one of our securities has an A region and a B region, but this is again just giving us a look at the actual aggregations, right? We initialized the counters for tomorrow all to 0. We've aggregated for this particular security. We can see we had 89 trades with this volume. And again, near real time. So these types of operational analytics, kind of canned reports, summary reporting solutions, very easily implemented using DynamoDB streams and Lambda. This is actually it's more than a database when you get to this point, right? What we're looking at now is a data processing platform, and that's really what I like to think of DynamoDB. So let's go ahead and execute our queries now. If we go back to our console, we can see we got a system here waiting for a transaction ID, right? That was one of our access patterns, query by transaction ID. I don't know what partition it's written on. If I go look at the data on the table, I can see it's each security sharded across 100 partitions. All I have is a transaction ID with prefixed with the security ID when I execute my query. So let's go ahead and see what that looks like to execute that query. When the user goes to look up a transaction on the table, this is the only information they have. They don't know what partition it was written into. So we're going to go ahead and provide that information, and we can use that algorithm we discussed in the presentation to decode the partition in which that transaction lives. So we can execute a single query to that partition 81 and get the actual item itself. If we want to get all the transactions for a given security, we just enter in the security ID, in this case S11, and we're going to query all 100 partitions for that stock or security and get 194 transactions. All right, so that's the aggregation pipeline that we were looking at there. Now, definitely come back. We got more for you in DAT 402. We're going to be going through, key optimization. How do I make sure my keys are well distributed across the table? We're going to go through partition level locks. If I need to have readers that are loading that I don't want writers interfering with while they're scanning their partitions. How do I lock those partitions and whatnot, and others that we're going to be looking at. So definitely come back for that session. We've got other sessions as well. We've got by our AWS data heroes, Alex DeBreeze here, the author of the DynamoDB book. Love seeing this content come out of the community. I'm no longer the only guy carrying this torch. We've got many folks. Jeremy Daly's another guy, does a lot of content in serverless. James Beswick, one of our solutions architects, producing a lot of content as well around this topic. Love all this stuff that's coming out of the community, and many others that I don't have time to mention. So please come take a look at these sessions, DAT 305, part 1 and part 2. Alex is going to be there talking a lot about some of his work, and thank you very much for your time today.